Above us and beneath us are structures far larger than the planetary system itself, and we have barely seen any of them. We know they are there from the paths of comets, from 2 spacecraft that crossed the edge, and from radioactive dust buried in the floor of Earth's oceans. But put it all together and one question remains. Where does the solar system actually end, and what shape is the bubble that holds it? That is the thing we still cannot answer. Start with the disk itself, because it is real. The planets do orbit in a nearly flat plane, and they do it for a reason that runs back to the beginning. The solar system was born from a vast cloud of gas and dust that collapsed under its own weight billions of years ago. A cloud like that never collapses perfectly evenly. It carries a faint spin to begin with. And as it shrank, that spin grew faster, until the whole thing settled into a turning sheet of material with the young sun blazing at the center. The planets formed inside that sheet, sweeping up debris along their paths. That is why they share a plane. We call it the ecliptic, and it is the reason every textbook draws the system flat. But flat only describes the planets, and not even all of them. Mercury rides about 7 degrees off the plane. Pluto, now counted as a dwarf planet, leans nearly 17. Long-period comets ignore the plane completely, falling in from every direction in the sky, and the disk itself is not lined up with the galaxy around it. The plane of the solar system is tilted roughly 60 degrees to the plane of the Milky Way. So when we say above and below the planets, we are not saying above and below the galaxy. We are cutting across it at a steep angle, carried along at something close to 500,000 miles an hour. Here is the part that unsettles people. In space, there is no fixed up or down, no floor, no ceiling. 2 astronauts drifting past each other can be head to head, and neither one is upside down. The ecliptic is simply a reference we agreed to use because it is convenient. But take that reference, point straight out of the planetary plane, above it and below it, and you do not find emptiness. You find shells. You find bubbles. None of them flat, and most of them never seen with any instrument. The map we actually trust ends almost exactly where the planets end. To understand why we cannot draw our own edge, we have to go back to a man who found the largest structure around us without ever seeing it, using nothing but the paths of comets. His name was Jan Oort, a Dutch astronomer working in the last century. He became fascinated by long-period comets, the kind that take thousands or even millions of years to complete a single orbit. And he asked a simple question: where do they actually come from? Not the orbits we measure today, which the planets have already tugged and bent, but the original paths, before they ever fell close to the sun. So he did the arithmetic. He took the cleanest cometary orbits he could find and wound them backward, and a pattern surfaced that was hard to explain away. The fresh comets, the ones falling toward the sun for the very first time, clustered around a single staggering distance, tens of thousands of times farther out than the Earth. And they did not favor the plane of the planets at all. They arrived from every direction, from above, from below, from the sides, scattered evenly across the whole sky. There was only one thing that pattern could mean. Surrounding the entire solar system, far beyond the last planet, there had to be a reservoir, a roughly spherical shell of icy bodies, billions upon billions of them, wrapping the sun in every direction at once. An Estonian astronomer had floated a similar idea years earlier, but Oort gave it the weight of real numbers. He had discovered a structure larger than everything inside it, and he had discovered it on paper from the trajectories of a handful of comets. The reasoning held. Decade after decade added support, and no serious rival explanation ever took its place. We named it the Oort Cloud. We now think it reaches out to something like 100,000 times the distance between the Earth and the Sun, nearly a quarter of the way to the next star. We think it holds trillions of frozen objects, with a combined mass of perhaps 10 to 100 Earths. And we accept every piece of that on the strength of comet orbits, because the most distant spacecraft humanity has ever launched, already decades into its journey and billions of miles out, would still need thousands of years just to reach the cloud's inner edge. So, the structure that marks the true outer limit of the Sun's reach is one no telescope has ever resolved, and no probe will touch for millennia, and it is only the outermost of several shells stacked above and below us. This is where it gets strange. Come back inward, to the bubble we actually live inside. The Sun is not quiet. It throws off a constant wind of charged particles in every direction, a thin spray of matter moving outward at hundreds of miles a second. We call it the solar wind. It streams past all the planets and keeps going, far beyond the last of them until it finally runs into the faint gas that fills the space between the stars. Where the two meet, the solar wind carves out a bubble around the whole system. That bubble is the heliosphere. It has structure of its own. First, the solar wind hits a kind of cosmic break called the termination shock, the place where it abruptly slows as it pushes against the pressure from outside. Beyond that lies a churning zone called the heliosheath, and the true outer wall where the Sun's wind finally surrenders to the galaxy is the heliopause. That wall is not a clean sphere. As the Sun plows forward through the galaxy, the front of the bubble is compressed, and the back is drawn out into a long, trailing region behind us. We know this boundary is real because we have crossed it. Two spacecraft launched decades ago to tour the outer planets simply kept going. The first reached the heliopause and registered the moment as a sudden 40-fold jump in the density of the particles around it. A wall of the galaxy crossed and recorded. The second craft crossed some years later in a different direction, and there the data delivered a surprise. The two crossings happened at almost the same distance from the Sun, even though they were separated by years, at times when the Sun's activity was very different. The boundary should have shifted between them. That stubbornness told scientists the heliopause is sturdier than they had expected, braced by a magnetic field in interstellar space stronger than the predictions allowed. And even past that wall, both craft are still deep inside the outer reaches of the Oort Cloud. We left one boundary and have not come close to the next. Interstellar space is not empty either. Right now, the Sun is drifting through a patch of slightly denser gas called the local interstellar cloud, a clump of material whose origin we still do not fully understand. It is not a flat band lying in the plane of the planets. It surrounds us in 3 dimensions, above and below. The raw stuff the heliosphere is pressing against as you watch this. Now, pull back further, and the scale jumps again. Our entire neighborhood sits inside a cavity roughly 1,000 light-years across, a region where the gas is far thinner than the galaxy surrounding it. Astronomers call it the local bubble. And we know how it formed because the evidence has been pieced together in detail. It was hollowed out by around 15 supernovae, exploding stars, the first of them going off some 14 million years ago. Each blast swept the surrounding gas outward and helped clear the space we now occupy. The Sun did not build this cavity. It wandered in from outside a few million years ago, and by pure chance now sits close to the middle. The bubble is still slowly expanding, and nearly every young star forming within a few hundred light years of us lies on its surface, pressed into being by the same shock waves the explosion sent out. This is not a story we have to take on faith. We have the physical evidence in hand. Buried in the crust at the bottom of the deep sea is a radioactive form of iron called iron-60, an isotope forged only in the hearts of exploding stars. It is unstable. Over a few million years, it decays away to nothing, so any of it found on Earth had to arrive recently from outside, long after our planet formed. And there it sits in thin layers dated to a few million years ago, lining up with the supernovae that built the bubble around us. The dust of distant explosions settled quietly on the ocean floor. Some researchers call this deep-sea astronomy, reading the history of nearby stars in the mud of our own planet. Go further still, above and below not just the solar system but the entire flat disk of the Milky Way, and you reach the galactic halo, a vast, roughly spherical region of ancient stars, dense globular clusters, and great quantities of dark matter, surrounding the galaxy much as the Oort Cloud surrounds the sun. Shell inside shell inside shell, each one wrapped around something smaller. And in the middle of all that detail, the most basic question of all stays open. What shape is our own bubble? And where exactly does it end? You would think 2 crossings would settle it. They did not. Both spacecraft left through the front of the heliosphere near its nose. We have no direct measurement at all of the long wake stretching out behind us, so the overall shape is still argued over. The older picture is a long tail trailing the sun, the comet-like form the field assumed for decades, but newer models point to something very different. A shorter, compressed crescent that one research team described as a deflated croissant. We genuinely don't know which is right. There is even an open question about whether the local bubble is a sealed cavity or an open chimney, venting up and out of the galaxy's disk into the halo above. Stimatios Krimagis, a scientist who has studied that boundary for decades, put it without softening. For 60 years, he said, we had the wrong image of the heliosphere, so consider where that leaves us. We can place the planets to within a kilometer. We can predict an eclipse 1,000 years out. And we cannot draw the outer edge of our own solar system. The heliosphere's true shape is unsettled. The Oort Cloud, which marks the real limit of the sun's reach, has never been seen and will not be reached for thousands of years. What lies above and below us is not the emptiness the poster implies, and it is not the tidy disk either. It is a stack of nearly invisible shells, inferred from the fall of comets, from 2 crossings near a single edge, and from dust in the seabed, all of it wrapped around a boundary we still cannot locate. There is one more thing worth sitting with before we close. The farthest objects in that outer shell may lie 1 to 2 light years away, tens of thousands of times the distance from the Earth to the Sun. Measured against that, our most distant spacecraft, for all its decades of travel and all the billions of miles behind it, has barely begun the trip. Picture someone standing in the middle of a continent who walks a few miles toward the coast. In proportion, that person has done more to reach the ocean than we have done to reach the true edge of our own solar system. We have studied galaxies on the far side of the universe in finer detail than the boundary of the system we live in. The thing closest to us is the thing we have seen least. The poster is not wrong. It is just small. The real solar system is not a disk. It is a set of nested shells reaching out toward other stars, and the true edge of it remains a question rather than a line. That gap is not a failure of science. It is the frontier, sitting closer to home than almost anything else we study. I have spent a working life pointing instruments at galaxies on the far side of the universe, and the thing I cannot stop turning over is not out there. It is the edge of the room we are standing in, the boundary of our own sun, still unmeasured. I think I have felt that since I was a boy with a borrowed telescope, the night the rings of Saturn first came into focus, and the tidy little picture in my head suddenly looked far too small. So, when you picture the edge of the solar system now, what shape do you see? And do you think we will finally draw it in your lifetime?